Okay. Welcome back, everyone. So we have in the next session, we will have three invited talks. And our first speaker is Dr. Philip Cardiff from the University College Dublin. And he will be speaking about the fluid structure interaction and the solid mechanics development using OpenFOAM. So before I hand over the mic to him, I would like to take this opportunity to introduce him briefly. So Dr. Philip Cardiff is currently an associate professor in the School of Mechanical and Materials Engineering in the University College Dublin. And he is very much well known for his contribution in developing the source code for solid mechanics and the fluid structure interaction libraries. And thank you again, Philip, for agreeing to give this talk with us. We are very happy to have you. And without further delay, I hand over the mic to you.
Great. Thank you very much, Chandan. And yeah, thank you for this invitation to speak at this nice event, hopefully the first of many. So yes, thank you for the nice introduction. My name is Philip Cardiff, and I'm an associate professor in the School of Mechanical and Materials Engineering in University College Dublin. So in this talk, I'm going to tell you a bit about this Solids for Foam toolbox, which I've been working on with some collaborators, which allows you to perform solid mechanics and fluid-solid interaction simulations within OpenFOAM. So solids for foam, what, why, and how? So what first? So what is solids for foam? Excuse me. Solids for foam is an OpenFOAM toolbox for computational solid dynamics and fluid-solid interaction. So for any of you who have used OpenFOAM before or who are familiar with OpenFOAM, you'll know that there are very limited solid mechanics capabilities within OpenFOAM. There are some basic solvers, but they're quite limited. So the idea is solids for foam will sit on top of OpenFOAM and add some additional functionality for solid mechanics and solid dynamics. And related to this, it'll also add some fluid-solid interaction capabilities. So for example, here's one of the cases I'll go through in this presentation. This is the dam break case, which you'll be familiar with, but this is the flexible version of the dam break. So you basically take the dam break interfoam test case from OpenFOAM, and then instead of having a rigid obstacle, you just make it a flexible object. So then the force of the falling water will cause the object to move. But also, as I said, you can use solids for foam for solid-only simulations, and in particular, I'm interested in metal forming when you have large deformation. So this is a large elastoplastic test case with frictional contact with large sliding. And a couple of years ago at the Cambridge OpenFOAM workshop, I was looking for something interesting related to Cambridge, so I found a bust of Isaac Newton online and decided to see what would happen if I simulated him bouncing around with some rubber properties, as you do. So this presentation, is relatively short, but if you want to learn more about solids for foam, you can go to the website, so www.solidsforfoam.com. So you can look around, and we've added tutorials there, and we're continually adding more and more tutorials. So it's just a toolbox you can add on to OpenFOAM, so you can see instructions there of how to install it, etc. So just to give you a little bit of extra information about the science, OpenFOAM is primarily a finite volume toolbox. So it's essentially a computational toolbox, so you can, people have implemented finite element or finite difference or other related numerical methods into OpenFOAM, but most solvers are using this finite volume framework. And similarly, most solvers in solids for foam will use a finite volume framework. So for most of you will have done some sort of stress analysis before, and a synonym for computational stress analysis is FEA, or finite element analysis. So finite element analysis is primarily used for stress analysis, but it just like the finite volume method that can be used for multiphysics. So in solids for foam, we're actually using a finite volume method to solve the solid mechanics equations. So it's actually very similar to finite element, so it's not a major difference. But just to give you some background, finite volume solid mechanics has been around for quite some time, back to the early 80s as the finite volume method was developing, even for fluid mechanics. If you look at even Nabla Limited's website, so Nabla, I guess, was the company to which commercialized foam, the commercial predecessor of OpenFOAM. You can still find their website on the Wayback Machine, so Web Archive. You can still find their own old website, and they actually advertised that foam had solid mechanics capabilities at that time. And then into the 2000s, various people worked on FSI and solid mechanics, and these are just some of them. And I was involved in a group that developed some solid mechanics solvers that went into foam extend, and then eventually all leading to solids for foam, which started in 2016. So what now? Why does solids for foam exist? So there's some desire to perform FSI or fluid solid interactions in OpenFOAM. More and more people are interested in FSI. So this is one approach to do that. But as you'll see in the talks today, there are many ways to do FSI with OpenFOAM. And also there's a desire to run solid mechanics cases natively in OpenFOAM as well, rather than using external finite element solver or something like that. Another motivation was having a modular approach to coupling different solid and fluid procedures. So this was before the foundation version of OpenFOAM introduced their modular approach. Solids for foam started to use a similar approach or propose a similar approach. And then also personally, I'm interested in research into numerical methods, particularly finite volume methods for solid mechanics. And then the how, what, why, now the how is it implemented? So the design motivation is if you can use OpenFOAM, you can use solids for foam. It's just another OpenFOAM solver. And at the moment, we're trying to primarily support the main forks of OpenFOAM, so openfoam.com, .org, and foam extend, but that's not so easy. And then there's an emphasis on following the OpenFOAM coding style. If you do any coding in OpenFOAM and you're not familiar with the OpenFOAM coding style, I suggest you Google it and look it up and try follow it. Just a note on how to support the different OpenFOAM versions. There are some differences between, say, foam extend and openfoam.com or openfoam.org. So the way that's supported is we use these compiler directives. So you'll see in the solids for foam source code that you'll have these compiler directives. If OpenFOAM not extend, not foam extend, then it'll use this line. Otherwise, for foam extend, it would use this line. Okay, and then solids for foam is a toolbox, but solids for foam is the actual solver as well. And there's just one solver, but that's a wrapper solver. And that just creates a runtime selectable physics model. And that physics model could be a solid model or a fluid model or a FSI model. And within each of those, you can have small strain, large strain, solid solvers. Fluid models can be things like pimple foam or interfoam or things like that. And then there's different coupling procedures. So it follows this modular approach. And as I just said, that last year, openfoam.org, the foundation version, has started to follow a similar modular approach. Not suggesting that they were motivated by solids for foam, but they started to follow this similar common software design approach. So now for the remainder of the talk, I'm going to go through a couple of example cases. So I'll start with one solid mechanics test case, and then I'll look at two FSI test cases. So this one is called narrow team member, and these cases I look at, they're a part of solids for foam. If you download it, you can try out they're tutorials. So this is a benchmark test case proposed in the literature. It's like an engineering component. It's called a narrow team member. So there's a symmetry plane here. It's fixed at the left, and you apply a pressure here, and then there's a notch cut out here to reduce the stress concentration. I'll briefly go over these, but I won't dwell on the equations. But essentially, we're assuming a small strains, and it's a linear elastic material. And also to point out in solids for foam, I said it's a toolbox for research into numerical methods for solid mechanics. So, excuse me. So there are various different types of solver that you could use to solve this. So you can use the kind of standard OpenFOAM approach, which is a segregated cell-centered solver. But also more recently, I've been working on coupled or block coupled implementations as well, both cell-centered and vertex-centered. But also you can look at fully explicit solvers. So there's various different ways to solve this equation that have different merits. Okay, you can compare it to, this is one paper from literature, Timofey et al. Who proposed it. For reference, Timofey or Ismet Timofey was the principal developer of Star CD, and the predecessor of Star CCM Plus, and he was particularly interested in finite volume solid mechanics. So okay, solves for foam gives the right results. Let's just look at a test case now. So if you're familiar with OpenFOAM, this should be familiar to you. You have a 0, a constant, and a system directory, so nothing looks different at this point. If we look through the 0 directory, if you're used to icofoam or piezofoam or pimplefoam, you'd expect a velocity and a pressure field, so U and P, but it's a solid mechanics, so we're going to solve for the displacement primarily. So we have a D field, and then we have different types of boundary conditions, but displacement might be prescribed like a fixed value, or we can have a traction condition. So in this case, there's this block solid traction boundary condition where we can apply a negative pressure. So positive pressure is pushing in on surface, negative is pulling out. And there's slightly different variants of this boundary condition depending on what type of solid model you use, whether it's segregated or block coupled or vertex centered. And then we can prescribe a displacement to be 0 on the left fixed hand side. And once again, there are different variants of this condition depending on the solver. And then we've traction free. And then if we move on to the scripts, so on solves for foam, there's an all clean and all run script in all the tutorials. Most of the time, the all run script just runs block mesh to create the mesh and solves for foam. But you can use external meshers as well. And solves for foam here with a capital F is the name of the solver. So the only difference, which is quite subtle between a solves for foam case and a normal OpenFOAM case, is there's a requirement to have a physics properties file. So this is one of the first files that are read when you run solves for foam. So this just specifies the type of physics model, whether it's solid fluid or fluid solid interaction. So that's the only purpose of this file. So it's a pretty small difference. If it finds solid, then it will look for a solid properties file. If it finds fluid, it'll look for a fluid properties file. And if it finds FSI, it'll look for FSI properties. And inside solid properties, this is where you specify the actual, let's say, solver, or it's called a solid model in this case. So you can switch between small train approaches, large train approaches, segregated approaches, block coupled approaches, and there's various different solid models. And they may have some settings like max iterations, etc. And just briefly to note, if you're not so familiar in solid mechanics, but in solid mechanics, you have what are known as geometrically linear and geometrically non-linear approaches. So if the deformation is expected to be very small, you can simplify your equations and come up with a faster, more efficient solver method. And this geometrically linear, this simplified approach, this small strain approach would be, let's say, the standard if you do a stress analysis in like SolidWorks or something like that. But there's many cases where the deformations are not small, and then you need a geometrically non-linear approach. So that can be specified here, as well as the details of the numerical method. Then for solids, you'll have a mechanical properties, and there's various different laws. So linear elastic being the most basic, you give a stiffness, Young's modulus, and a Poisson's ratio that governs how much the material contracts in the transverse direction. And then things like gravity and other settings like that. Okay, so let me move now on to the first FSI test case. So this is this flexible dam brake I showed at the start. So it's just a normal dam brake, except now we have a flexible obstacle. The equations, this is the standard interfoam equation, so multi-phase volume of fluid approach. The solid will use a similar approach before, except now we have a mass by acceleration term, so it's a dynamic problem. And then the additional equations are at the FSI interface, you have what are known as kinematic and kinetic conditions or constraints. So that basically says that the velocity of a piece of material on the fluid side of the interface has to equal to the velocity of the solid material at the interface. And the displacement of the fluid material has to be equal to displacement solid. So this means that the materials cannot overlap and you can't have a gap between them. And then the kinetic constraint says that the forces must be equal or equal and opposite, or the tractions equal and opposite. Here in this case, I'm using the same unique normal defined in one particular direction. So when you have an FSI procedure, its goal is to try and force those two conditions. So the approach implements solves for foam, and which is common in literature, is this partition approach. So you solve the fluid, then you solve the solid, and then you iterate if desired. And then when it converges, you move to the next time step. But also in literature, you can find monolithic approaches, and that's where you construct one large linear or linearized system and solve it all in one go. So this has been something I've been working on for the last couple of years, but recently I've actually funding to work on it. So hopefully this approach will appear in solves for foam in the coming year or two. And then just a note on parallelization. In solves for foam, we use this global polypatch at the moment. So we keep a copy of the entire interface on all processors. I won't go through all the details here, but just to point out the difference between an FSI case in solves for foam and a normal OpenFOAM case. So you'll be able to see it straight away inside zero consonant system. We now have a fluid and solid subdirectory for each of those. So essentially, this sub-region or this region fluid, the fluid boundary conditions are inside zero fluid. The solid boundary conditions are inside zero solid, and similar for the material properties and the system settings. So it's like two OpenFOAM cases in one. And then when in physics properties, we specify fluid-solid interaction, and that forces this FSI properties file to be read, where we can specify the coupling method. I'll quickly just look at it here. So this is the case in ParaView. So if I look at, for example, the alpha field, so when you load it in, you'll see that the fluid mesh gets loaded in and the solid. So in ParaView, we can use this extract block filter to just say extract the fluid, so we can get the fluid on its own. And then if you play the fluid, you'll see it drops and your obstacle will form. And then we can extract it a second time to get the solid out. In this case, we're using a small train approach, which is a non-moving mesh approach. So you have to use this warp by vector filter to see the actual warped solid. So you can see the geometry here of the obstacle is a little bit different than the standard InterFOAM case. And if you go to the website, more tutorials, fluid-solid interaction, and flexible dam break, you'll see it's trying to match this particular version of the case from literature where people like to benchmark their codes. Okay, so then the last thing I want to discuss is this 3D tube test case. So this is also a common benchmark in literature for FSI. So you have a flexible pipe fixed at both ends, and then you apply a pressure pulse. It's also called a water hammer case. And then you monitor the displacement of some point on the inside of the pipe wall, called point A here. So you can find this on the website discussed as well. So it's an interesting case because it's sensitive to the mesh and time step discretization. So this is showing if we use a first order Euler discretization with a large time step and then make the time step smaller and smaller and smaller, you can see that it's starting to converge, but it's first order. It's like a big gap between each of them. We can also use a second order time scheme, so the backward second order scheme for both the solid and the fluid, and then you can see it converges much more quickly. If I superimpose both of those, you can see that a relatively large time step with the second order scheme will give similar to a very fine time step with the Euler scheme, which is as expected. And even though I haven't gone into the details and I'm running out of time now, there's various different ways to implement partition coupling. So Dirichlet-Neumann coupling is the standard approach, but there's also this Robin-Neumann coupling, which is a not intrusive coupling approach, not a black box method. So these are available in solves for foam as well. And you can have different acceleration methods like the Atkins method or the inverse quasi-Newton method. And the fluid model, there's literature that suggests that if you have a weakly compressible fluid, then it will help the FSI convergence over a fully incompressible fluid. So for example, in this case, you can use at least 6 different test cases or approaches to solve the problem, including an external coupling library you may be familiar with called Precise. So I'll quickly jump through these because I'm out of time. But you can check, you get the same answers, but you can monitor the number of FSI iterations required for conversions. So generally, the inverse quasi-Newton methods work better. But if you have a sufficiently small time step, then this Robin intrusive coupling method can produce quite low numbers of iterations. Okay, and that brings me to the end. And just acknowledge various funding bodies. And also, I was fortunate to get one of these ERC grants last year. So I'm actively looking for postdocs and PhDs to work on it. So if you're interested in FSI and cardiovascular flows and OpenFOAM, then feel free to contact me.
Thank you very much, Philip. As usual, very insightful talk, and thanks for sharing it. So quickly, because we are slightly out of the time, I will take few questions, but these questions I think are very interesting. So one of the two queries merged together is that, could you please elaborate a bit on the parallelization part, and is solids for foam the new integrated version is parallelizable, and how is the scale up of this solver?
Yeah, good question. So the way it's parallelized at the moment is probably not a very good way. So if you have decompose the fluid and decompose the solid, say into 50 cores, then core number 0 has one part of the solid interface and has a different part of the fluid interface, and they may not overlap. So a naive solution is at each point before we do the mapping, we sync an entire copy of the faces and points at the interface, do the mapping, and then take the part you need. So that's probably okay up to like 50 or 100 cores, but it should be changed to use something more like AMI, the way that maybe it's a decomposed mapping. And I think that can be done. It's just on the list to-do list. So it does run in parallel at the moment, but probably the scaling past 50 cores is not going to be amazing. So for really large cases. So that's something that would need to be fixed.
All right, thank you. And another interesting question was that, how does solids for foam work with two interacting solids with fluid? So I think the question is directed towards if you are planning to include some sort of friction model, etc. So what's your take on that?
Yeah, so you can, at the moment, it is generalized that you can have as multiple interfaces, but I guess I can think of some types of problems that you might be talking about, say like in cardiovascular flow, if you have a heart valve and it's hitting off another heart valve or off the wall of the vessel. So that means the fluid domain is disappearing. So what they do in literature is they use immersed boundary methods or something like that, and then you implement a frictional contact. So that's not included at the moment, but I'm involved in some projects on heart valves, and this is something we want to do. So I think it can be done, but integrating probably immersed boundary methods is the way to do that. And I've seen on GitHub, there's various people who have worked on this with OpenFOAM. So yeah, thanks so much.
Thanks, Philip. So due to the restriction of time, I would basically thank the speaker again. And thank you again for joining us, Philip. And we will go forward with the next talk.
Yeah, no problem. Sorry for going a bit over.
Yes. So basically, we have our next speaker with us, Dr. Timofey Mukha. And before I just hand over the mic to him, I would just briefly introduce him. He is presently a postdoctoral researcher in KAUST in Saudi Arabia, and he is basically now the chair of the Turbulence Modeling Technical Committee of OpenFOAM, and he is quite well known for his pioneering contribution on the turbulence models. So without further delay, I would basically request Timofey to present his work with us. Thank you.
Thank you, Chanda. Can you hear me?
Yes, we can hear you. Can you please share your screen?
Yes. So I think you might have oversold me there a little bit, but nevertheless, thank you very much for the introduction and for the possibility to speak. Do you see my screen now?
Yes, perfect. We can see you and
hear you. There should be some, where is it? This one. There we go. Is it good now?
Yes, we can see it.
Perfect. Then I start. So yeah, thanks again for inviting me to talk here. It's really been a pleasure to listen to all these wonderful talks. So as Chandan already said, I'm a postdoc here at KAUST, and this is going to be a presentation of a joint work with my PI here, Matteo Parsani. And I'm going to talk about high Reynolds number simulations with OpenFOAM using essentially scale resolving methods like LES, or something I call Quasi-DNS here. This is something completely new. I haven't presented this anywhere yet. And in fact, some of the simulations have finished a couple of days ago. So something very fresh. And the motivation for this here comes from two directions. One is that I've been for a while involved with both OpenFOAM, but also the high order CFD community. And it's a little bit funny that there's this kind of dispute between these two communities. If you talk to high order people, they'll say you absolutely should not use a low order solver like OpenFOAM to do LES or DNS because everything will get smudged, you can't resolve things, and so on and so forth. And if you listen to the finite volume people, they say, well, when you're doing LES, you're not anyway in the asymptotic regime where your formal order of accuracy is valid. So it doesn't matter at all if you use a second order solver or a fifth order or whatever. And this go on, for years, and it will continue. There's nothing to do about that because people want to be a little bit defensive about the stuff we use. But as I said, I use both, so I'm sort of impartial here. To me, it's a little bit interesting to see the benefits and sort of the minuses of both approaches. But from the OpenFOAM part, I was thinking, could we, now that we have a little bit more computational resources, we have a new computer here at KAUST, run a classical benchmark such as channel flow at a higher Reynolds number, where we start to see all of the effects of scale separation and the stiffness of the whole problem, and see how good of a result we get. This is by no means groundbreaking science, but it's more of a curiosity. But there's also the second perspective here, and I think this ties nicely into the panel discussion which we
Timofey,
had.
are you?
Yes.
Sorry, are you changing the slide? We still see the cover slide.
Oop. Okay. Yes, I am, but I haven't moved much. How about now? Maybe it's because
now
of the
we
full
can
screen.
see it.
Let me
Yes,
let me
now we
check
can
going
see it.
back. Can you see the first one now?
Yes,
And now the second one.
yes.
All right, so we're going to sacrifice a bit of real estate on the screen so that you actually see the slides. It's not a big problem, and you haven't missed much here. It's just some bullet points. But yeah, the second perspective here is that I wanted to create some kind of good entry point for people who are starting out with LES, so that there's some case files, and also quite important, all the post-processing script to generate various quantities which you see in papers which dwell deep into the analysis of turbulent flows, like spectra, quadrant analysis, 2-point correlations, all of that stuff. It takes a little bit of time to figure out how to actually compute those, even when you're a bit familiar with the theory. And then maybe produce some publication which is a bit more sort of novice friendly in terms of how the text is written, where we motivate the case setup and the various choices, and discuss the quantities and so on and so forth. So these are the two sort of background and motivation perspectives. There's two highlights in the literature which I would like to talk about. One is this very nice paper by Razarevesh et al. In Computers and Fluids, and they also do channel flow at Reynolds tau 550, so not very high, with OpenFOAM and NEC 5000, which is a high order solver. And they look at various mesh resolutions, and the spoiler, so to speak, is that the NEC is more accurate, which is perhaps not very surprising. But the more interesting thing in that paper is that they look at various quantities that you want to get out from your simulation, and they look at these portraits of the errors in these quantities in the delta x plus delta z plus plane. And essentially what you see is that for each quantity, you would get essentially like a line in this parameter space where it is exact. For example, for u tau, you have like a whole set of resolutions where u tau is precisely accurate. But then if you move away from it, even if you move away towards better resolution, you might get a worse u tau. And then you have those things for all the quantities, and they are not necessarily the same. They're different for each quantity. Of course, there is a general trend that things get better towards refinement in the end, but until you're really in the very, very high resolutions, things are all over the place. So this is just a very nice illustration of how difficult it is to kind of reason about what resolution is necessary and so on and so forth for these type of simulations. And the other publication is actually my very first publication as a PhD student. Back in 2015. And this also was about LES of channel flow with OpenFOAM at a pretty low Reynolds number. And I know that this one has received some attention as sort of an entry point to LES because I have provided the cases and the results online and so on and so forth. And since I was a beginner myself, I think the text was also a bit more beginner friendly because I tried to explain, stuff, well, perhaps to myself most of all. So in some sense, what I'm doing now, what I would like to produce is somehow a second iteration of this report in some sense, but at a higher Reynolds number with more quantities and a bit more experience from the first author, basically. So what we're going to look at here now is this channel flow at Reynolds 1000. Channel flow looks like this, in case you've never seen it. So this is a snapshot of a velocity field from the best mesh I ran at. So it's a classical turbulence benchmark. The reason being that it's periodic in both X and Z, which makes it very easy to set up. The flow is driven by an external force, and in OpenFOAM there's a utility which allows to sort of control this external force such that you get a bulk velocity which you set. And the bulk velocity is essentially just the mean velocity across the whole geometry of the channel. Then you have to select the dimensions for the directions in which you have periodic conditions, and they should essentially be large enough to fit all your structures. Here I select something which I would probably say like a moderate size for this Reynolds number, and here delta is the half height of this channel. So for meshing, we use like a free block approach for meshing in the wall normal direction, which was developed by a fellow PhD student back in the days when I was a student as well. And it's essentially works like this, that you have one block with constant resolution in the viscous sublayer. Then you have another block with constant resolution in the outer layer. And then you have essentially a third block which just connects the two. Okay, so it's pretty simple, and I mean, it's motivated by the physics, and it's easy to set up in block mesh. So with this particular mesh, I realized after the fact that maybe the ratio here between the size of the cells is a bit too large. It's actually 1.21 between these largest cells, which we'll see will cause a slight trouble, but this is by no means, radically huge or whatever. So it's still completely valid. And we will run on 3 meshes. So the coarsest one is M1. And here I show the wall parallel resolution in inner units. So 4024, this is coarse. And then M2, I refine all 3 directions by a factor 2. So we get this in the wall parallel directions, which is already pretty good. And then finally, M3, I refine again, but only in the wall parallel. So then you get essentially something which is close to a DNS mesh in the wall parallel directions. And if I would refine in Y as well, then it would be a pure DNS mesh. But the case becomes too large. So this M3 grid is 200 million, just for reference. So this is where this, quasi-DNS terminology I use is essentially for the M3. So it's not really LES and not really DNS. It's something in between, I would say. And for schemes, we can aim for best accuracy here, so we can use linear interpolation for everything. We don't need any non-orthogonality corrections because everything is perfectly orthogonal. We use a PISO solver with 3 inner loops, which is sort of a pretty standard approach. For the linear solvers, I use just the simple CG. For the pressure, I use the CG with diagonal incomplete Cholesky DIC preconditioner. It's really easy to set up. There's not 10,000 parameters like with a multigrid, and it scales well. So I think it's a solid, robust choice. For this largest mesh, we are running on about 4,000 cores. And we can do this thanks to our new computer here at KAUST, which is called Shaheen 3, which has been put in production very recently, maybe less than a month ago. So this is the first project I'm doing on this machine. So far, quite happy with it. So we're first going to look at some basic statistics on the different meshes. So here is just the mean velocity and outer and inner scaling. And what we see here is that on the courses grid, we don't really capture the friction velocity well. So in the inner scaling, things get, shifted upwards. So clearly the sum1 grid is not good enough, but that we've sort of known already. There's not a lot of difference between M2 and M3 for this particular statistic. But if we move to the Reynolds stresses, then we actually start seeing the benefit that the gray curve corresponding to M3 is capturing the peak better, both in this streamwise component and also in the vertical component. So now we see that there is actually a benefit to refining in the wall parallel direction. A little bit unfortunate, we have this under prediction here in the streamwise stress in the outer region, but it is what it is. As I said, if I would refine it, then it would be a DNS mesh, right? So I've also looked at vorticity fluctuations, which is not very often looked at, but I think it's a good benchmark because it's still just the based on the mean flow, but it's on the gradient on the mean flow, and that's always trickier to get. And also each component of vorticity involves two components of the velocity, so you kind of get cross-component interaction there. So I think the results are actually quite good. I'm happy with this. So we have a bit of an underprediction in one of the stresses in the buffer layer region, but it's it's not severe. I think for this quantity we're doing a pretty good job. And now we're going to look at only the M3 mesh results, but at a bit more kind of, let's say, fancy statistics. So this is, for example, the budget of a turbulent kinetic energy. So essentially the magnitude of the different terms you have in the budget of that equation. And there is a nice utility here provided by Janus Hopman to compute this. So I've used that and I recommend it. Something we may note here, so in this plot, the dissipation is sort of minus the dissipation, so it becomes positive, which means that in the log layer, we expect that it starts coinciding with the production term, which it clearly does for the DNS, that's the black lines. And for our case, we see that it doesn't. So the dissipation actually underpredicts it. And instead, we have still this viscous term, the gray line, all the way up to here. So this is a little bit disappointing because I think like the fact that you have this so-called equilibrium in the log layer is one of the results people sort of know about well-bounded flows and expect to see. So yeah, maybe we need a bit more resolution to actually capture this well. Then we can also look at the so-called premultiplied spectra, which is essentially a power spectral density, and then you multiply the power spectral density by the wave number. So you essentially get an equal distribution of energy across each band here in this logarithmic scaling. And these are from different normal locations. And I think these results are really nice, but you see that for the largest scales, I think we're getting some aliasing and somehow an enhanced peak at this location. And my feeling is that it's maybe due to the domain size not being large enough. And to illustrate this, I have this 2D plot of the same thing, but now we are looking on the x-axis. This is the wall normal direction, so the further from the wall to the right. And here we have the wavelength in Z. So all of these spectra are in the spanwise direction. And this is the DNS, so the reference. The Lee-Moser DNS, by the way, I don't think I mentioned which DNS is. It's the most, most widely used channel flow DNS, I would say, the Lee-Moser 2015. And we see this inner peak here, and then here we see sort of what will eventually become the outer peak at a higher Reynolds number, but it's sort of a beginning of it. And then you have this region, this diagonal region, which corresponds to the so-called wall-attached eddies. And this region at the higher lambda z, which includes the outer peak, is generally said to be populated by these very large-scale motions, VLSMs. And if we go to the LES results from OpenFOAM, we see that in principle everything is captured pretty well except for this large-scale motions. And I think that that's where my presupposition about the domain size being a little bit insufficient comes from. That maybe they're so very large that they didn't fit in my domains, so you got some aliasing effects and we would need essentially to increase the domain size to get the spectrum properly in this upper side of this plot. Okay, so then I also wanted to try out very quickly a solver which is called RK-SymFoam, which is provided also on GitHub, also on Janus Holtmann GitHub repository. And it introduces a couple of new things. So first of all, it uses Runge-Kutta for time integration, and I used this second-order implicit Runge-Kutta scheme, but there are many other available. I used this one just because it's sort of similar in properties to the backward scheme used for pimple foam, also second order, also implicit. Then they have a symmetry-preserving convection discretization scheme. And then what I rather diffusely write here, other improvements to make the solver less diffusive. I just don't want to say something which is not exactly accurate because I'm not an expert in all of this stuff. But in principle, I think the innovation is that you have less diffusion coming from the pressure velocity coupling. But I refer to the papers which can be found in the repo for the details. And I just show one results because I don't have time. I simulated on the M2 mesh, and this is a comparison between the blue curve is pimple foam and the red curve is this solver. And essentially, you don't really see any amazing improvement, unfortunately. Maybe you can claim this stress is computed a little bit better, but it's remember what I said about one must be very careful about looking at the error at a particular resolution. It just may happen that for this solver, yes, at this resolution it's a bit better, but if we move, things change. And also, if one looks very, very closely, one doesn't really see it in these plots. But if one looks at this point, remember I said in my meshing strategy where I have perhaps a little bit too large jump in the resolution, you can see that there are some oscillations in the stresses coming from the RK-SymFoam. They're not very large, but they're there. So that tells me that the solver is actually quite sensitive to how you build the mesh. I mean, very sensitive, it seems. But maybe there's probably some settings one can tune to sort of control the balance between how much you sort of aim for zero diffusion and how much you aim for stability. It also takes longer to run. So I don't have like a figure right now, but I think it's about 1.5 times longer to run the case compared to pimple foam. So conclusions, I hope that this would be the most thorough validation for channel flow to date, and also the highest Reynolds number at this resolution. I may be wrong, but I think this is the case. The overlap of DNS is obviously not perfect, but it's not really to be expected since we did not run a DNS. The quantitative agreement on the best mesh, I think, was quite good, and qualitatively we could definitely see all the features of the flow. Maybe those very large scale motions were not there, but it's not because of OpenFOAM, it's because of a domain. Running a DNS would actually be tempting to see if we can, take that final step. But I estimated it to be around 4 million core hours, which doesn't, it's too much to just check this if we get a better overlap or not. So I don't think I'm going to do it unless these 4 million somehow fall on me from somewhere, which I doubt they will. And I mean, it's sort of my subjective take about the high order dispute. I think for this quasi-DNS resolutions, right? If you're going that refined, you might as well run a high order solver. You'll probably get better results, honestly. But of course, it's also offset by, can you actually run a high order solver for your case? If you're running a channel flow, you definitely can. If you're running something much more complex, and you have like a whole workflow set up in OpenFOAM, you should not stop yourself from running your simulation because it's a second order solver or something. You can get perfectly valid results. Maybe if you want to study the evolution of, if you're studying transition or something like extremely sensitive, then yeah, you probably should do high order. But for most of the stuff, it's perfectly fine. This can be disputed, but this is where I end. Right. So thank you very much for your attention.
Thank you, Timofey. It was very, very nice talk and very insightful. For the interest of time, I will quickly take one or two questions. So basically, the first question the audience has asked, for the quasi-DNS in OpenFOAM, are you using laminar model? and which discretization order do you use for temporal and spatial discretization?
Yes. So all of this is with no SGS model. Exactly. I'm also running a case, the M2 grid with the Sigma model, and I actually hope to show it today, but it's still running. I need a few more days. I don't expect things to change. This is my prediction, but I know that people would be interested, so that's why I want to run it. But no, this is fully implicit LES, and the order is second for the schemes.
Right. And the next question quickly, that can you comment a little bit more on whether the Navier-Stokes equations were decomposed in any way? And if so, what type of decomposition was used?
No, they're not decomposed. So
Right.
we're essentially solving because there's no SGS modeling. So no.
All right. Thank you again. So let's thank the speaker again.
Thank you very much.
Thank you for joining us. And let us then move forward and welcome our next speaker. I think we have our next speaker with us, Dr. Liang Yang from Cranfield University. Could you please unmute yourself and switch on your camera, Liang?
Can you hear me? Hello.
Yes, we can hear you.
Brilliant.
Thanks for joining. Thanks for joining and agreeing to give the talk. So before actually he starts with the talk, let me introduce Liang. So Dr. Liang Yang is actually a lecturer in the Cranfield University, and he mostly actually works in the marine renewable energy systems, and he belongs to Center for Energy Engineering there. So without further delay, I again thanks Liang for joining us and continue with this very interesting talk on a new capability of meshing for accelerating OpenFOAM workflow. The floor is yours, Liang.
Thank you. Thanks for the invitation. So probably I give a very different talk on the introducing the meshing capabilities we've developed for years. So initially it was developed for speed up our own workflows when we're trying to using some meshing some complex shapes and putting on our could be wave energy or could be the shape simulation or wind turbine simulations. But then we eventually found, okay, this one could be useful for many people. So then we have this very different meshing ideas. And later I'll introduce you what it's about. Also, based on this, actually, we form a spin-out company from Cranfield, and actually it's currently supported by the STFC's program. So, okay, so we can start. What is the mesh? So first one is motivation, is we're trying to provide alternative mesh generator for general geometries in OpenFOAM. We know currently the OpenFOAM we have the SnapHex mesh, which is actually is very easy to use, but sometimes we find some difficulties. So we're trying to develop our own solver, own mesh generator. And we're trying to export it directly as polymesh files that OpenFOAM users can use it. One of the key features that that we're trying to develop, actually, we can present on the right. You can see in the figures. We're trying to develop something that is most of the volume is occupied by the hex domain mesh or could by voxels. And near the boundary, there's only one or two layers of the mesh, which can be deformed or can be attached to the surface, so that we're trying to keep the main structures as hex, which is quite actually one of similar to the SnapHex mesh, but there are some new features we introduced in. So in terms of the mesh, I'm not sure. I try to have an over background introduction about what's the current meshing technologies we have in general. The ones actually used by most of commercial codes, we call it commercial codes or open source available. We call it a bottoms up method. So most people, I think when they start meshing, they start meshing with the points, edges, and do the surface mesh. After they do the surface mesh, they build the volume on that surface. So it is adopted by most commercial companies. The advantages of that approach is they can provide extremely high quality meshes because that's through the surface to volume strategy. But there are also some disadvantages. Well, if you're following that one, that needs the perfect geometries as CAD or STL files need to be perfect. They need to be very closed. They need to be closed geometry. You just spend a lot of time on clean up the geometries, fill the holes, like fill the gaps, removing the unnecessary features from the geometry. This is typical if you're going to the industrial workflows, and that's for once. But think about you have built this for some in the iterative process. So you do this again and again. So that's why actually most engineers, CFD engineers, spend 90% of time actually spending on the meshing. Just so that's something really pain. And another disadvantage of this using this bottoms up method is that it's very difficult to parallelize in distributed memory. So that's one of the disadvantage, and also hard to create very coarse meshes. So if you want very coarse meshes to start with, that's difficult. There's another group of people. They are working on the overlaid grid method. I think the SemHex mesh also belongs to this category. The good thing about this type of method from the volume to meshes is that it's a tolerant to better geometries. It's fully automatic, so the users don't need to specify too much things. And another very good advantage about this feature is that it can be distributed run on distributed memory with domain decomposition. It's very straightforward to implement that, and can make very coarse mesh. So that's very good. But another disadvantage is sometimes the quality is very bad actually near the surface because it was directly projected from the volume to the surface. So our idea is just how to improve that small low quality meshes on the surfaces. So we spent a lot of time on that. So the strategy is something like this. General workflows is look at this. First, we have the physics geometries. This physical geometries could be STL or could be anything, or could be the CAD exported as STL. And then we create a signed distance function from the physics geometries. So if we create these steps, one of the good thing is that if depends on the resolution, if there's a resolution is smaller than the threshold, then it's automatically features all the small features you don't want. If you increase the resolution, then the features can be captured. It also can automatically fill the holes, fill the gaps, etc. So that's very good for cleaning up the geometries. So that becomes this process. If you convert it to level set or signed distance function, then the good thing is it clean up the geometries. And the next one is just we can have the boundary modification. You can have cut cell, you can move the nodes, you can do whatever you like, and you have one or two layers of the unstructured mesh near that. So this is the general workflow. So I'll give some examples. This is one examples for the external flow. We build up. This is the flow over the simple sphere and also a very simple box. Okay, so this is the OpenFOAM. Okay, we do have a front end package for that, but depends really on the feedbacks. We're trying to make it as command lines as well. So okay, after a few resolutions, okay, this is something you can see. One of the good thing is actually is it can keep the. I'm not sure whether I turn on the features on, but we can capture the thing, the sharp edges quite well. This is one, And this also based on octree-based mesh. So we can have the octree behind, so we can have octave mesh refinement. And the ones on the right is the internal workflows with just cylinders. The same strategy happened. And then let me check what's the mesh looks like. Yeah, so it's uniform mesh with you can see that one of the good thing is that I'm not sure whether they have already done in SnapHex mesh. We can capture the sharp edges very easily. You can look at the cylinders. We have sharp edges there. This is one example. The other one of application actually is in trying to make some in a biomedical image application. So from CT scans, we can convert it to the ST, create the STL, and from STL, we just create the mesh. We just figure out all the workflows. And it's very nice OpenFOAM simulations with our ChopMesh. You can see that the boundary the boundary part is clearly captured. And then another 3D problem heat exchanger. That's similar as this biomedical application. But there's one thing I'm trying to emphasize here. Actually, the heat exchanger, the geometry is not from STL. The geometry is from the sine distance function directly. So depends on the input files. We're trying to support different input files. So one of the things we're trying to create is if we have directly implicit geometries, then we don't need the create the sine distance steps. Okay, this is another example showing the photon reactor. This is a quite challenging problem because we have small buffers there, small gaps there. These gaps in these geometries is only 0.1% of the total length. So that's the CFD results. If you look at these buffer elements, this is just some inflow. But let's look at the meshes here. The gaps is very well captured. If you zoom in, you can see how well the boundary geometry is captured with our generator. So this is another example showing the floating wind simulations. You can take a close look at our geometries mesh generator. We do have octree refinement with different layer of color with different colors, and sharp edges is captured. And we have the overset mesh. This is actually the overset mesh, but the overset mesh, the total volume actually depends on the surface, on the distance, because we do create a sine distance function. So we basically remove the rest invariant parts. So the whole overset mesh, the whole total number of the meshes is reduced. And also, I forgot to mention another advantage of this type of things, this type of meshes, because it's hex dominated or it's vox dominated. We have very small number of elements compared to fully unstructured meshes. So that's advantage. This simulations is actually on our Archer 2 in UK's HPC's computing image computation in last year. You can find them on the internet. Another thing I would say is a bit challenge for this type volume to surface mesh is capture the trailing edge parts of the geometry. So I'm not sure if you try to implement or try this geometries in the SnapHex mesh, probably you get some very strange shapes because this trailing edge is actually very hard captured by traditional volume to surface approach. So what we do actually is we subtract the STL with the thin edges and combine them with level set so that we can model these thin features correctly. So you can think about our approach is most of the approach is the volume to surface approach, but in some small parts, we take the surface meshes from surface to volume ideas. So it's like a combined method to dealing with this type of trailing edge problem. So this is, okay, this is another, this is this trailing edge example with the overset mesh, with the boundary. You can see the edges captured quite very easily with the OpenFOAM simulation. Another good feature is that we do have the parallel domain decomposition approach. We have a very ideal, because one of the difficult parts of the meshing algorithm is that it's very hard to parallelize. So we do have a parallelized approaches. So that's through domain decomposition. So there's another feature, there's another example showing that because we are doing a volume to surface mesh, one of the good things is there very less input for the users. We just specify the minimum voxel size. So this is the typical NACA benchmark problems with if we think about minimum elements we have is resolution around 4,000 times. You can read these figures. It's very large geometries. But with our parallel things, we can just achieve this by 5 minutes time in 100 cores. So it's very extremely efficient. And this image actually is from the meshing competition in this year in the US. So there's two mesh competition. One is the sketch, one is the statue. The other one is a crab, the author from image files. So scan image files. So the one of the this project actually can be used very suitable for the biomedical image-based simulations. So I think that's more or less that's something we're trying to introduce. So conclusion that we basically read STL files or read science function directly. It can be automatically removing the gaps, overlaps, and there's small features. We have the options to keep the sharp edges and C edges by considering the traditional surface to volume strategy. We have Octree in behind is fully parallel. We're trying to have an online release in this year. I think it should be free to use and just upload your geometries. This is what I thought. If you can, you're welcome to follow us on the LinkedIn page on our company's website. It's a spin out from Cranfield, supported by STFC. So thanks. I think that's all the information I'm trying to give. If any questions, you're free to you can find me easily on the website. Just drop me emails, or you can ask me any questions after this presentation. Thank you.
Thank you very much, Liang. So it was very insightful and very new thing for at least me to learn. So due to the interest of time, I will just go through a quick couple of questions. I think you have already mentioned that you will release an online version, will be free to use. So basically another question is that, is this a cut cell approach or not? That was one of the questions.
Okay, that's great. It's very similar to cut cells, but the cut cell, okay, I'll say it's a big improvement to cut cell, because if you directly prove the cut cells, there are very small elements, small edges there. So we're trying to keep the smallest elements more or less the same size as the smallest voxel size. So keep the current number we don't, sometimes we try to have explicit solvers, so we're trying to keep the minimum size of the element is to be similar size as in a reasonable range. So you can think about this as cut cells, but
okay.
Yeah.
Got it. Yeah. So the next I think, interesting question is it compatible with dynamic or sliding meshing techniques?
Sliding mesh. Yes.
Yeah, or dynamic
Because
meshing techniques.
we
Yeah.
do have that sliding mesh is basically we create there's a sliding mesh or that one it goes to another. It's called multi-material things. If you have multi-material, when you're trying to do the either sliding mesh or you're trying to have a conjugate heat transfer problem, you're trying to have a solid mesh and the a fluid mesh which is have a transferring information. So yes, it will have that capabilities, but there's no currently I don't have a demo case for that, but the first thing we're trying to do is a conjugate heat transfer.
Right. And another follow-on question on that was that can you use adaptive mesh refinement?
Yes. So currently we have octroi based. So if you're trying to have octroi, if you have adaptive mesh on the particular interest region, just divide by because most of them they are voxel based. So just divide by half, divide by just split into 1 to 8. So that's type of things.
All right. Thank you very much, Liang. And let's thank the speaker again from on the behalf of all the audience. Thanks for joining and sharing your knowledge. So I think we will take a short 5 minutes break now because we are running out of time. So I will be here and we will actually continue with our next 3 invited talks, the last session of the day after 5 minutes break. Thank you very much. So I request all of you to stay tuned with us. Rahul Haldar, our next speaker. Rahul, can I request you to try to speak and unmute yourself?
Uh,
Right.
yeah,
Okay.
you can hear me?
Yes. We can hear you. So let's wait for 2 more minutes. As I told, we'll take a
Sure,
5 minute.
sure.
Sure. You can try sharing your screen in the meantime.
No, I cannot share. It's the sharing option is
All right.
disabled.
Because there was some problem in
Just give
making
me
your
1 minute. I'm trying to fix it.
Okay, sure.
You should be able to do this now.
Yes, I can share it now. Is it visible now?
Yeah, perfect. You can make it full screen. So let's wait for 1 more minute and we'll start.
Sure.
All right. Welcome everyone again to the last session of the day. And we have 3 invited talks in this session. And our first speaker is Dr. Rahul Haldar. He's a postdoctoral research associate in mathLab in Italy. And today he will be speaking on coupling physics-informed neural network with OpenFOAM. Thanks, Rahul, for accepting our invitation to share your knowledge in this symposium. The stage is yours. Thank you.
Yeah, thanks, Chandan, for the invitation and also nice introduction as well. Okay, so today I'll be talking about coupling physics-informed neural network with OpenFOAM. And this is a work in collaboration with Giovanni Stabile and Professor Gianluigi Rozza at SISSA MATLAB. Okay, so a bit of background before I move forward. So there are so that we come to a same page, what type of works we are currently carrying out here and what is the directions we are moving ahead to. So in the left-hand side, there are several types of classification of reduced order model. So reduced order model is a computational approach to expedite the numerical simulation. So on the left-hand side, we have projection-based approach. So what we do, we project the governing equation on a reduced space and try to solve the governing equation in the reduced coordinate itself. So we have a platform called Ithaca FV, which is coupled with OpenFOAM, and Giovanni Stabile is the main developer of this platform. And then there are data-driven approach as well. There are several works available, and also there are several open source platform available in the MATLAB group. So you can have a look. And and then next approach is that it's a marriage between these two, data-driven approach and projection approach, which we call it as a hybrid approach. So one of the hybrid approach that I will propose here, and we call it as a discretized P. And the bit of the work you can find it in this archive paper that we put in the last year. So if we look at bit of the timeline, so back in 2017, majority of the reduced order model were linear algebra based because like the one I told, projection based reduced order models, we project the governing equation on a reduced space and solve them there. And in the 2017, artificial neural network came as a reduced order model. But here we try to completely remove the physics and try to approximate the parametric space or the temporal space using different data-driven approach. So since we completely remove the physics, so it is the solution accuracy depend on the richness of the data. And to circumvent this issue if there is a sparsity of data. A seminal paper came out in 2019, which is Physics Informed Machine Learning. So from last year onward, we started to think, can we take the residual from the we are existing open source CFD solvers, which is in discrete version of the PDEs, and can we take it as a physics residual in the OpenFOAM? So question is that why this pin? What is the motivation of such work? So if we look at the pros and cons of the forward solvers we have, such as OpenFOAM, that I am going to couple it with. So, and also several other open source platform as well, which use finite difference, finite volume, finite element, discontinuous Galerkin, etc. So they are physics based. So one of the good thing about that, they are good for well-posed problems. But since at every parametric point you have to run the full simulations every time, it is expensive for repetitive task. But given the solution accuracy, given the like discretization scheme, it can be highly accurate predictions. But again, because of the time consumption at every parametric point and high fidelity simulation, it is difficult for real-time analysis. On the other hand, if we look at neural network approach, if you have data available, be it coming from high fidelity data or experimental data, so you can approximate the parametric space using different data-driven approach. So once you have approximated the parametric space, now it is very inexpensive to move around the parametric domain. So it can be used for different design optimization and control application, etc. And then so another issue that I have already told, but the prediction accuracy depends on the richness of the training data set. So the marriage has been done between these two streams by using different the pin approach. Let me tell you some brief of this physics informed neural network. How does it work? Those who are unaware of it. So there is in the machine learning, we have an output and inputs like t and x, time and space, and the output u is some kind of algebraically has an algebraic relationship with the input. So that's why we can compute the derivatives out of it. So what we do, so we compute the spatial derivatives and temporal derivatives from the computational graph, and we put it as an extra loss penalty term in the loss term additional to the data-driven loss, and that is how we can actually get rid of the sparsity of the data, and we don't have to do any compromise in the accuracy. So we started to think that why write down an extra equations using which is coming from automatic differentiation. On the other hand, since we have a fixed forward solvers to solve our forward problems, why don't we use the physics exactly coming out of it and try to use them for developing my machine learning model for prediction at a particular parametric point or say temporal point, for solving several inverse problem, in-post problems, or if you want to predict very quickly to move around the parametric space, whatever my objective is that the neural network serves, but my physics-based loss term will come from exactly the forward solvers that I have used. So that's the objective of mine. So I'm not going to compete any other existing pin solvers. Probably every day new pin solver is coming, but this is my straightforward objective of development of such work. And so that it becomes very industry friendly as well. So because they are already using some solver for forward solver, so they can use that for prediction purpose as well. Another advantage is that it's a flexibility of input choice. Since you are not computing the derivative from the computational graph, so t and x no longer necessary to be in the input. So you can take any other input in your deep learning network as well, and you still can couple the physics that is coming from OpenFOAM or whatever it is solver. So as I have told, that in the forward solver can be discretized in a full order way, or else it can be projected on a reduced space, and you can take them as a residual in the physics as a physics-based loss term itself. So let's look at what is the full and reduced order. So I will quickly go through these two slides just to give a brief of introduction. So any kind of nonlinear Gowan equation, you can discretize it in any of your favorite implicit or explicit way. You can use any kind of your time discretization. And then in the typical CFD simulation or typical forward solver, you march in time. But usually it takes longer time given the degrees of freedom of your variable does have. But if you want to project them on a reduced space, then the governing equations can be solved very easily, because now your variable is now small s, which is a smaller degrees of freedom rather than your higher degrees of freedom u, and phi is the basis vector set on which you have projected your governing equations. So there are several ways of computing the phi. So one of the very famous way of computation of these basis vector sets is proper orthogonal decompositions, and you can project the governing equation on the reduced space. Some extra modification is required for the nonlinear term called hyperreductions. Given everything is done, you can again evolve in this reduced governing equation just the way you have done for the full order CFD simulations actually. So that is one way of treating solving PDEs, be it in the full order model or in the reduced coordinate. But in both the cases, you have to evolve in time, or you have to do some iterations in your parametric problems, in your steady state problem, whatever. So now question is that, can we solve this PD in a different way? That can we take the residuals coming out of projection based ROM and we solve it in the pin framework itself? The advantage is that once we have trained them, so then we can predict very quickly in a real-time way at a parametric points, and we can move very easily on the parametric space, and so that it can be used for design, optimization, control several problems. So that's the framework. So you take the residuals, instead of evolving in time, you take it in your optimization loop, which is a machinery in the in any machine learning frameworks. So I have used ANN and LSTM for closing the loop, and this is two types of pin framework we have proposed. One is called ANN DSpin, which is coupled with ANN, and another one is LSTM DSpin, which is coupled with LSTM. And some small results with Burger's equations, and it shows that both NN and DSpin perfectly captured, perfectly match with the numerical simulations that you have, whereas the conventional pin does not match well with your numerical data. It does not mean that they are wrong solutions. It just does not mean that same discretization scheme you have not used in your pin solver. That's why it does not have any responsibility to match the numerical data that you have. That's it. On the other hand, since you have used the same discretization scheme in your pin solver itself, both the NN and LSTM pin exactly match. So here what happened, here both my CFD solver and my pin solver are written in PyTorch. So PyTorch, so the computational graph is retained, and that does not cause any problem for different solver environment. Like if one is in C++ and one is in PyTorch, that kind of problem does not arise here, since both are in PyTorch and computational graph is retained. And same thing also I have done. I have first projected on a reduced space and then considered it as a residual for your pin solver. And it has enhanced the training time a lot. It's several orders of magnitude. So that's the part we have finished while coupling two solvers in the same environment. Now questions, can we couple pin and forward CFD solvers coming out of different environment? Means if your CFD solver, just like in our OpenFOAM, it is in C++, and our machine learning solver in PyTorch or TensorFlow, so then the issue happens that computational graph breaks. So let me tell you, what does it mean that computational graph breaks? So in case of pin type of solution platform or any machine learning platform, so we have to compute the gradient of certain type. So one while computing the physics-based term that we consider as a loss penalty in the additional to the data-driven term, so from the computational graph itself. So there, y-predict is the output of the neural network, and we have to compute this kind of spatial and temporal derivative so that we can compute the physics-based loss term itself. And on the other hand, there is additional term that you need to compute, which is in the gradient descent optimization algorithm. Once you have computed the loss, you have to take the derivative with respect to the hyperparameters so that you can update your neural network hyperparameters. So let's see what we have so far now, what we have got rid of, what are the problems we have. So in case of DSPIN, this derivative computation is no longer our burden because we have completely offloaded it to OpenFOAM or any other external CFD solver. However, in conventional PIN, it was there. But on the other hand, this gradient of loss term with respect to the parameter, both the DSPIN and conventional PIN, you have to carry out. So if the computational graph were retained, means both the solvers were same in the PyTorch platform, so then you can easily compute this derivative using automatic differentiation, which is super fast. But since both are now in different environment, now this become an issue. So if you want to apply some derivative schemes like finite difference, then it's hugely expensive. So now let's look at how to compute these derivatives in a more efficient way if my external solver is something else other than my PIN solver. So that's the platform, what we do while doing the gradient descent optimization. So I have my data-driven loss terms, which is like imagine a situation where you have an input, which is time dependent in a problems. It can be time or any other observations, which is varying over time. And you have output, which is like in case of your Navier-Stokes equation, pressure, velocity, etc., or in case of Burger's equation, you have U. So, and imagine that you have data available at few temporal points, and you take the prediction and subtract it from and take the distance from the actual value that is available to that, and you make a mean squared error and try to minimize that, which is basically your loss terms coming from data. And on the other hand, if you look at physics-based loss term, you pass the Y predict to your CFD solver, and it give it back the residual associated with your continuity equation, momentum equations, or whatever residuals that is numerical, whatever residuals that is arising from your governing equations, it give it back. So now you add these two terms and try to update the hyperparameters at every epoch from this formula, where it is necessary to compute the derivative of the loss term with respect to the hyperparameter. But since, as I have told, it becomes a bottleneck if the computational graph breaks and you cannot compute it using automatic differentiation anymore, and if you want to do it using finite difference, it becomes tremendously expensive. So now let's look at how to reduce the expense of it. So if we now take a derivative, which we need to do in case of for this kind of gradient-based optimization problems. So if you take a derivative of this Ri square, it becomes 2Ri del R by del P. And if you make a chain rule with respect to Y prediction, I will tell you what is Y prediction with respect to the small prediction later, but it comes chain rule, it becomes like this. So now what is the problem of directly computation of this? It is, first of all, it is detached from computational graph because it is now coming from OpenFOAM or whatever any external CFD solver, but it is a dense matrix because R is globally dependent on the parameters, neural network parameters, and that's why you cannot compute it using finite difference. Every epoch iteration, if you need to compute this Jacobian, it will be extremely expensive. On the other hand, if you compute the residual, which is coming from say momentum equations or any kind of governing equations with respect to the variables like pressure or velocity, it's very sparse matrix. And because they are locally dependent on the variables, and it can be easily computed. It's similar to like tri-diagonal system or something like that, which can be easily computed without much effort using finite difference. And on the other hand, the other part, it is coming from the automatic differentiation because YPRED is a outcome of the machine learning platform. So that's why this is.
Can you
Yes?
please summarize? We are actually almost towards the end. Yeah.
Okay. So this is the modified loss terms that we have proposed. So I will quickly go through the OpenFOAM part. So what we did is that Ithaca AB is a derivative of OpenFOAM, and we have coupled it with physics-informed neural network. And what happens in OpenFOAM, that AN and BN, these are the system matrix that we can get import from the OpenFOAM. And for linear and nonlinear system, you have to, for linear system, you don't need any loss correction. For nonlinear system, you have to do this kind of loss correction I have told. And so this is the platform. You have actually coupled it with OpenFOAM in the Ithaca FB. You can very well use this kind of OpenFOAM operator. So these are all open source platform. You can have a ask me if you need further details. And it has been applied for Laplace equations as well as the Burgers equations with this loss correction. It's perfectly working well while taking the residuals from the external CFD solver like OpenFOAM. Yeah. And
right.
so now we are coupling with Ithaca FB with PINA, which is our platform in OpenFOAM for reduced order model and physics-informed neural network. Thank you. Thank you.
Okay, thank you, Rahul. Thank you for accepting our request and sharing. It's very interesting and futuristic work. I'm guessing that a lot of questions will arise, but for the interest of time, I'll just take one or two questions quickly. So the first question has been asked by Angelina. What is the reduction in computational time when doing a direct parametric CFD study compared with your data-driven approach?
Okay. So if you are the potential of this kind of physics-informed neural network is realized in the prediction phase. So if you want to solve the Burgers equation using CFD, it will probably take a seconds. On the other hand, if you want to solve it using PIN, like the forward problems, so it will probably take in the range of minutes or so. So, but now if you want to predict at a different parameters, say like I have trained it for different mu's and I want to predict it for something called mu x or mu, which was not in my training phase, there it is a fraction of second. So there you can have a lot of computational gain as compared to the full order models. So it is almost real time once the training is done. So that's your answer. But if you want to solve the forward problem using such kind of optimization technique instead of evolutions, then of course it is even this is more expensive than solving a conventional CFD approach, but it is much more quicker in the prediction phase where it has the potential of, because I want to move around my parametric space very smoothly.
Thank you. For the interest of time, I will again thank the speaker on behalf of all the audience. And if you have any further question, please reach out to Rahul. I'm sure he will be happy to answer your doubts and queries. Thank you again,
Sure.
Rahul.
Thanks, John.
So,
Thanks, Chandan, again.
Let's move ahead with our second presentation of the session. So our next speaker is Mr. Rajdeep Adak from IIT Bombay, and he is currently working as a research associate in FOSSEE. So Rajdeep, can you please unmute yourself and switch on your camera maybe?
Yeah, hello. Am I just going to do an audio check?
We can hear you, but we can't see you.
Oh, okay. I'm so sorry. Okay. Is my camera visible right now?
Not really. Can you try sharing your screen?
Sure.
Yes, we can see your screen, but your camera somehow is not working. Anyway, that's not, yeah,
Okay.
now we can see you.
Okay.
Perfect. Now you can see you. So please go ahead and share your knowledge about the OpenFOAM GUI. Looking
Thank you.
forward to it. Thank you.
Sure. Thank you. So thank you so much for having me here. So I am currently working as a research associate here at FOSSEE. So I kind of began working here back in 2021 as an intern. And the project itself was about creating an OpenFOAM, creating a GUI for OpenFOAM. This tool later on kind of got renamed, and we have named it as Venturial. It's a Python toolkit to expedite the process of generating OpenFOAM cases. And so just a little bit more about FOSSEE before we move on to talking about the tool. So FOSSEE is a project here at IIT Bombay, where we intend to reduce the dependency on proprietary software, and we want to diversify the use of free and open source software in academia and research. We have various different projects inside within FOSSEE, and the one that I work in is in the OpenFOAM graphical user interface team. So some of the activities that we very frequently here do involve, like lab migration, textbook companion projects, and several workshops. So these sort of projects really help proliferate the use of open source tools in academia and research. So coming to our OpenFOAM GI project. Well, the idea kind of began with the thought process that when we try to model a case in OpenFOAM, we often use it. Yeah, we often directly use text. Why not just do it graphically? And we also realized that it is very difficult for beginners to kind of understand how the texting syntax of OpenFOAM works. So something like that can be really made productive if you can do this thing graphically. So the OpenFOAM GUI project kind of originated from the works of Deepak Surti back in 2016, where he had created a software called Reynolds. And then we started the work again in 2021. This time, this tool was kind of like re-envisioned with a newer tech stack, and we utilized Blender, OpenGL, and Python primarily. Our tool is also available here on GitHub, so you're free to just go and look at it. We often post stuff about the tool's usage on GitHub as well. Lastly, on a separate note, OpenFOAM GUI is part of the CFD FOSSEE project, so you can go and look up onto things that we also do, which is directly related to OpenFOAM and more related to the safety part of OpenFOAM. So that you can look into on this particular website, which is mentioned on the left corner of the screen. So what does our tool do? So this tool helps us create an OpenFOAM workflow. It has a single homogeneous UI that where you can do meshing, solution modeling, and you can run the solver execution within the same UI. It has multiple entry points. You can even still write text if you want to. It enables you to make your workflow very reusable, and it's very agile. In meshing, we support CAD-like geometry creation, and we have several tools which enable a very easy to use interface. We also have tools for solution modeling, and some of these tools come with predefined models, so you don't really have to create your own models. You kind of have a template on your own, and you can customize that template as much as you want. And finally, for execution and running, we have several tools that help you set up your solver and customize the solver parameters. And lastly, you can run OpenFOAM with internal commands, and you don't really have to type the commands themselves. All the workflow is kind of like, the error handling of the workflow is done preemptively. So a lot of the things where you need to run OpenFOAM to see the errors is really not required in our case. So this is how the interface of Venturial kind of looks like. On the start page, you have a very nice project manager, and you also have like a memory that is attached to the software. So that if you lose some of your progress, you can just go back to the memory and see what was the latest step that you have done. On the bottom right corner, you can see we also come up with some of the interactive tutorials. So and that's a part of the software. So you can directly click on those tutorials, and the software will help you use the interface and move through the tutorials. Okay. So let's look into the capabilities of the meshing part. So here we have some of the ways in which we can do meshing and very easily compose. So this is a simple block mesh tool of a combination of hexahedral primitives. And you can very easily join them and unjoin them. So the capability of writing the block mesh dictionary is increased. So you don't really have to worry about creating the block mesh dictionary by your own hands. So these are like some of the blocks that we are just joining, and then we can even edit them very easily. That's through the process of decomposition. So this really makes your meshing tasks pretty easy. Secondly, we can acquire a lot of information about the geometry. So if you want to know about the vertices and the way they are oriented, because OpenFOAM has rules for, they have stringent rules for handling your geometry. So you can do all of those things within the software, and it will acquire all the information that is required for the block mesh dictionary to work. So this is the one that you see here is acquiring the information about the vertices and in the order in which OpenFOAM can understand them. We also have ways in which you can assign the patch types to various different walls so that you can customize your geometry. And we can also define curved edges. So these are some of the latest work that you see here, where you can create a curved geometry out of a single hexahedral primitive, which normally consists only straight geometries. We support all the types of geometries that are there inside OpenFOAM right now. And you can also view the results on ParaView by just clicking a Run ParaView button. On the right side, you can see some of the complicated geometries that we have recently tried and try to build them, because the rendering of Blender and the rendering on OpenFOAM is not really the same tool. So we really had to write some of the code ourselves to make sure that it exactly replicates what's there for OpenFOAM. We also have a snappy hex mesh dictionary generator, which is kind of in the process. It helps you very easily import geometries into Blender, and then it automatically builds up the patches and the boundary layers for you. So you can very easily do this process as well. But this is not there in the latest version because it's kind of under development. So I'm probably assuming that by the end of the month of July, you will probably also have this feature as well. But all of this is like really possible because underneath we have a Python API which kind of does the majority of the heavy work. So the way this kind of works is in OpenFOAM, dictionaries are defined with C++ source code, and we look up their dictionary definitions, and we created a alternate inside Python. This alternate of OpenFOAM dictionary, which is basically a C++ dictionary, it's basically an analog of the OpenFOAM C++ dictionary. And that analog works here in Python. And you can exactly do the same process for manipulating an OpenFOAM dictionary in a Python environment. The API itself is called PyVNT, and it has several capabilities. One of the things that we found was very useful with the PyVNT API is that scripting with OpenFOAM becomes very easy with PyVNT because you don't really have to write a lot of source code. Second thing is everything is having its own definition of classes, and the class definitions are very easy to read and document. So they are basically the same process that you're when you create an OpenFOAM dictionary out of C++ source code. You don't really have to worry about going through the documentation of OpenFOAM to understand what it is that you have to write. You can go through PyVNT's documentation, and PyVNT's documentation will help you very easily write OpenFOAM source code with much fewer lines of code, of course. We also have within PyVNT several wrappers of the OpenFOAM source code. So OpenFOAM kind of has some case management tools like Foam Search and Foam Dictionary, and we have made them available inside PyVNT as well. So this is one of the tools that we basically, we are running a test file here, so you don't see the name of the tool. But the idea with the test file is when you run the test file, whatever code that is there in C++, it can directly be read into a Python environment, and it is displayed here. As you can see, we are reading an FV solution file, and we can see the FV solution file kind of displayed as a tree here. And the same thing can also be created using text. So it's not very difficult to write the code for the same thing. And you can see that within not more than 5 lines of code, we are able to write a section of the solution file. Again, the wrappers of the OpenFOAM case management tool. This is a form search wrapper. You can directly use a Python command in the virtual environment to run the form search wrapper. And we're just trying to run a particular parameter within the FE schemes file. And you can see that I think the name of the parameter is DD schemes. So we just want to see the default value for the DD schemes here. And this is also a feature that is directly available. So, and lastly, this is another new feature that we're kind of working on. Here you can see that if I have an OpenFOAM dictionary, I can import it into our environment, and you can directly see them as a graphical system. So I'll just hold on pause over there so that, yeah, there it is. So you can see how we can vary these parameters very easily. We can hold on any of these nodes, and then you can go on towards the left side where you have different tools to manipulate them. This is also kind of a thing which is presently in the works, so you don't really see the final version of this, but I'm presuming that the final version of this is going to be far better. We also have proactive error identification and execution control, and all of this is there under a section within Venturial called the run utilities. So like the design inside Venturial itself is very well written, of course. And the reason why we put a lot of effort behind design is because we wanted the graphical interface to be made dynamic and interoperable with other Python tools as well. Because nowadays in CFD, there is a increasing involvement of different tools so that you can solve more complex CFD problems. And we realized this early on, and we knew that we needed something which is very capable of, making it scalable. And we made everything scalable by using object-oriented programming. So on an end note, I would say that our project itself, while initially it was meant to become a graphical user interface, but now we are kind of going more towards comprehensivity. We want the software to not only be interactive, we want it to be scripted as well. And there are several benefits that are involved in the software that it helps people to use OpenFOAM in a Python environment. Second thing is it makes learning OpenFOAM very easy for other people. And there are several features that are going to be involved up in the future. So I would really say that the project is kind of definitely going somewhere, and we really love the idea of using an interface as well as having this capability to script within the same environment. So we love the symposium. We so far have seen several different projects. We have workshops available. We have internships, jobs for students, and you can go over to our website there and see. We also have like the workshops are conducted usually in the month of January, sometimes in between of like maybe in other months as well. And one of the videos regarding the 1 hour long tutorial of how we use our software for a very specific case within OpenFOAM is also there on YouTube. So you can just go on over to this link here, and that link will help you find the video as well. So that's all about it.
Rajdeep, can you please summarize? Our next speaker needs to join from USA.
Yeah, that's all about it. Thank you so much. So I really like the audience, and I would like to know if there are any questions.
There are a few questions, but however, we are really tight on the time because our next speaker has to join from USA. So I think you can reply. Could you please reply to
I will
the questions
definitely
in the
reply
chat?
to the questions in the chat. Yeah, thank you.
So let's thank the speaker, and thank you very much for giving this insightful talk, and let's move forward. So I request you if you could answer the questions in the chat box.
Sure, thank you.
Okay, so then let us move forward with the last talk of the session. And let us welcome Professor Sumanta Acharya. And before he goes ahead with sharing his knowledge with us, let me take the privilege to introduce him briefly. And he is currently the program director of NSF and a senior professor in IIT Chicago. And he has an experience of almost 40 years in CFD. So thank you, Professor Acharya, for accepting our request. We are really looking forward to your talk. Without further delay, I would request Professor Roy to kindly say a few words, and then Professor Acharya can start his presentation.
Hi, sir. How are you doing?
Good, Somnath. I'm just trying to see if I can share my screen.
Just see if you can share your screen. Professor Acharya has more than 40 years experience in computational fluid dynamics. Is one of the leading personalities in computational fluid dynamics now, and he has vast experience in several applications, including turbine cooling and other thermofluid applications. So, so please present your. It's visible. It's visible. We can see your slides.
Okay, great. And you can hear me properly, right?
Yes,
We can hear you.
Okay, perfect. All right, so I'll get started in the interest of time. My talk is going to be very simple. I'm not going to talk too much about OpenFOAM. I'm just going to talk about the applications of OpenFOAM for two different applications. I chose these applications partly because they're quite different in nature. One deals with turbine vane cooling, high Reynolds number, transition to turbulence, has extreme demands in terms of the mesh requirements. And the other, which is a more recent effort, deals with data center cooling or CPU, GPU processor cooling that looks at evaporative two-phase cooling of conductor chips, semiconductor chips. So I have to acknowledge the contributions because the work is primarily of the PhD students. Yosef Kanani, who did the work on turbine vane cooling, finished his PhD maybe 3 years ago or so, and is now working in a rocket engine company over on the West Coast. And the current ongoing work from Karthik Upadhyay, who's looking at semiconductor chip cooling. So the outline is very simple, as I mentioned. I have a one-slide overview. Then I'll mostly talk about the turbine airflow heat transfer, mostly from the work of the Yosef Kanani as a PhD student, and then I'll talk, just briefly introduce this topic of evaporative cooling that we're currently doing work on. This work is still in progress, and then I'll conclude. So just a little bit about OpenFOAM. We are using OpenFOAM extensively in our group. In the past, we used to have our own in-house code that Somnath and other students have used, but OpenFOAM provides good versatility, provides excellent scalability, which was one of the main reasons why we decided to go with OpenFOAM, because of the scalability, since many of our computations require high resolution and high computational effort. And then also gives you the opportunity of providing let's see, providing a range of submodels in the code. And it also allows you to incorporate new submodels for improvements in the submodels to be incorporated. This last feature is very important for us because we want to, OpenFOAM doesn't necessarily have all the submodels and all the schemes that we want to incorporate for our calculations. So we want the flexibility, just like in a source code, to be able to include our submodels and any modifications or change that we want to make. So both the scalability and the ability to program in submodels and algorithms, etc., was important, which is why we are using OpenFOAM. So the first application is turbine vane. It's a fully or highly resolved calculation. So we are basically solving the Navier-Stokes equation with either no submodels, which is the direct numerical simulation, or we are solving the filtered equations with a subgrid stress model, which means it's a large eddy simulation. So we mostly do DNS or LES at the higher Reynolds number. So these are Reynolds number of the order of 10 to the 5 or 10 to the power of 6, approaching a million. On the other end of the scale, we are looking at low Reynolds number flow, looking at semiconductor chip cooling. And here we are looking at liquid cooling of the chips, which is now becoming of increasing interest because of the higher power density of the CPUs and the GPUs. You recently saw NVIDIA introduce the Blackwell chip. These units now are approaching almost a kilowatt in power, and so they really need some kind of liquid cooling, either single-phase liquid cooling or two-phase liquid cooling. So here we're looking at evaporative chip cooling, and here we are using the volume of fluid methods. There are other approaches you can use, but here we have chosen to use the volume of fluid methods, and we are solving for the liquid phase, which could be either water or refrigerant. We are solving for the vapor phase, and we are solving for the non-condensables, like the air, for example. What we have done here is because the surface wettability plays an is important for the physics of the problem and how the contact line evolves and the evaporation takes place. We have included a certain contact angle model. In this case, it's a Kistler contact angle model. It's a dynamic contact angle model. So there is a little bit of model in there with some input parameters. And we have also included a model for the evaporation dynamics here, and I'll show that briefly. So two different applications, two different Reynolds number ranges, and that's what I want to show you. So just very quickly about the turbine cooling problem. So this shows you the combustor and the first stage vane and the turbine. And it's well known that in order to increase the power, you have to increase the rotor inlet temperature. So you can see as you increase the rotor inlet temperature, the power goes up, which means that designers are trying to push the exit temperature of the combustor to as high a value as possible. These days, 3000 degrees 15 of the order of 1200 to 1500 degrees Celsius exit temperature our current designs, particularly for military engines. So you can see the high pressure vane and the rotor downstream sees very high temperature and well beyond the material limits of the materials that typically nickel alloy that are used here. And so these have to be actively cooled using bypassed air from the compressor stage and routing them over the airfoil. So the cooling is an important problem. So there are a lot of complex designs for cooling as shown here. So this is typically a design that we have explored. So there is internal cooling, impingement cooling, pin fin cooling inside, and there's film cooling here, which is shown by these green lines. I won't talk about the various cooling strategies. We have worked in all of those areas, but I'll just talk about the external aerodynamics, uncooled, external aerodynamics, flow, and heat transfer. So we'll probably talk about vane. We'll not talk about the rotor here, just vane and end wall heat transfer, the secondary flows. I'm not going to talk about film cooling. So these are fairly complex problems because there are a number of complicated factors here. The stagnation region here shown here is important because you have a high heat transfer here and the initiation of the secondary flows in the passage. You get a horseshoe vortex here that propagates as a secondary flow into the passage. So that's important. You have flow acceleration on the suction side and also some on the pressure side. The flow acceleration on the suction side leads to laminar to turbulent transition, so you have to account for that. The free stream turbulence coming out of the combustor exit can be significant for gas turbine combustors, can be in the range of 5 to 15%. And so you have to account for the free stream turbulence and its effect on the heat transfer. There are other complications like surface roughness and surface curvature that I will not talk about here. Secondary flows, in the end wall, as I mentioned here, you get corner flows and you get passage flows. So the secondary flows are important. You can see the secondary flows here along the end wall. transition to turbulence, you can again see the transition to turbulence here. It occurs somewhere around here where the flow breaks down to these finer scale structures. So being able to predict the transition process. And you also see unsteady streaky structures, although the flow doesn't transition to turbulence here, but these unsteadiness affect the heat transfer. So I'll talk a little bit about that. A little bit about the computational details. Here, as I said, we have used OpenFOAM. We have used a range of grid points down from about 10 million to about 180 million. This depends on the spanverse domain of the calculations. If you do the full domain calculations, including the involves, then you need the higher resolution approaching 180 to 200 million grid points. In some cases, in order to look at things like transition, we are able to focus only on a specific span, let's say half span of the Vane, not the full domain, and we impose periodic boundary conditions on the boundaries of the spanverse domain. So then in that case, you can use lower resolution grid points. These calculations have been done on CPU clusters, and we have varied the number of CPU processors from 500 to 3000. We have tested the scalability of OpenFOAM up to about 1000 processors, and it's pretty good. It's almost linear up to that point. As you go to higher and higher number of processors, some drop of its scalability because of communication latency is expected. We have done these calculations for 3 different turbulence inflow parameters, Reynolds number in the range of 500 to a million. I'm showing you the 500,000 Reynolds number case. Boundary conditions there. And as I said, we are looking at a single Vane with periodic conditions on the 2 sides as shown here in this figure. So some quick results. These are the pressure distributions. We have good experimental data, so we can compare with experimental data. So this is the pressure coefficient. This is the stagnation region, suction side. So you can see the flow acceleration. This is the velocity. So you can see the flow acceleration on the suction surface here. Laminar to turbulence transition on this surface. And you can also see some flow acceleration on the pressure surface. But the agreement with data is pretty good. This is an important result. This is hard to predict. Most computational simulations would not be able to predict this. This is the Stanton number, the heat transfer, looking at 3 different turbulence levels. Low turbulence levels of 0.7, higher turbulence level of 8%, highest turbulence level of 12%. Symbols are all experimental data. Lines are our predictions. So this is the lower turbulence levels. This is the stagnation region. This is the pressure side, and this is the suction side. So basically, you can see at the low turbulence level, it's mostly laminar flow. So you have the boundary layer, the heat transfer drops up. Some transition unsteadiness very close to the trailing edge that you see a pickup in heat transfer. But the 2 higher turbulence level, you definitely see the transition process occurring. So for 7.9%, you see the transition taking place around 0.8 S by L. And then the flow transition to turbulence, and you get the pickup in heat transfer. This is hard to predict. And at a higher free stream turbulence, the transition occurs at an earlier point. And again, you can see our predictions, which are the lines, are directly on top of the measurements. And so we get excellent predictions, partly because of the highly resolved calculations we're doing. On the pressure side, its flow is mostly laminar but unsteady. And so you can see the effect of the unsteadiness, which increases the heat transfer. I'll talk a little bit about this. I don't have time to talk about this. So a little bit about the computational detail. We have used only half the Vane span, so we can use lower number of grid points. So we're using between 30 and 50 million grid points because you're using only half the span. We're using an LES model here with a subgrid stress model to resolve the unresolved scales, the subgrid stresses. And we've done this calculation for 8 flow-through times so that to get the statistics we are averaging for 8 flow-through times. and across the periodic span of the domain. So these are just some computational domain. I'll quickly focus a little bit on the pressure side. It's a little easier to talk about it, much more physics on this side, so I don't have time to talk about this. So I'm showing you here the pressure side Stanton number, heat transfer instantaneous, pressure side Stanton number instantaneous, lower turbulence level of the top plot, higher turbulence level on the bottom plot. And I'm also showing you the instantaneous streamwise flow velocity or instantaneous streamwise turbulence velocity fluctuations, if you want to call it. And you can see there's a strong correlation, particularly here. You can see wherever the velocity fluctuations are high, you get a higher heat transfer. So this is just showing you the correlation between velocity fluctuations and the instantaneous heat transfer, which is captured much better in this joint probability density function between the Stanton number and the velocity fluctuations. You can see this joint PDF is basically linear, which talks about the strong correlation between velocity fluctuations and Stanton number. Just some results, but I'm not going deep into these results at all. This is the suction side transition to turbulence. Again, the Stanton number, leading edge, the suction surface. This is the transition point, and you can see the increase here. This is the Stanton number. The lighter shade shows you higher Stanton number. So these lighter shades are higher Stanton number. And this is the velocity fluctuations. So here in the velocity fluctuations, you can see the transit. These are turbulent bursts that you are seeing here, and these break down into these finer scale structures where the flow has transitioned to turbulence. We are showing you the velocity profile here in non-dimensional coordinates, u plus and y plus. This is the fully turbulent profile here. And so these are the velocity profiles here in this region, starting at 0.6, which is somewhere mid-span, 0.81 and 1.21 now approaching the trailing edge. And you can see as you approach the trailing edge, the flow profile goes towards the fully turbulent profile, but it's not fully turbulent. So you're getting transitional flow in this region, and there's a lot of interesting physics that's going on, which we have described in papers that we have published. So then I quickly talk about the full Vane calculation. So now I'm including the end walls here, and when you include the end walls, you get this complex flow passage structure being initiated from the Hershey vortex here that splits up into a passage flow and a corner flow. A lot of literature on this topic, so I won't belabor the point. But just a little bit about the computational details. Now we are using many more grid points, almost up to 180 million grid points, because we need the resolution because the domain size is larger, and then we have to resolve the end wall regions because of the boundary layer and the vortices that are on the end wall region. So these are done with a much finer mesh resolution. We do have some good experimental data here with a collaborator, Forrest Ames from the University of North Dakota. So we have good temperature and heat transfer data, let's say on the suction surface in the region which is shown here in red. And so here I'm showing you measurements on the top row here and predictions on the bottom row here. These are Stanton number. These are plotted as a function of S by L. S by L is this axial length here along the blade chord versus Z by L. Z by L is the span-wise dimension along the Vane span. Okay, so I'm showing you the Stanton number distributions in this red patch, measurements and predictions. At best, we're expecting qualitative agreement because there is high uncertainty in the measurements. Of course, these are difficult measurements to take at these higher turbulence levels. These, I think, are at 7.9%, 7.4% turbulence levels. So there's a good bit of uncertainty in these IR and wall temperature measurements, but nevertheless, the agreement with measurements, qualitative agreement with measurements and predictions are quite good. You can see we are capturing all these high temperature streaks, and the magnitudes are in good agreement. I can show you better the quantitative agreement here. The solid symbols are the experimental data, uncertainty bars are shown, the lines are our predictions. These are at two different axial lengths plotted as a function of the Vane span. So this is the end wall, and we are going up the Vane up to about a quarter of the, not quarter, up to about 0.25 Z by L. So it's probably about half the Vane span. And this is the Stanton number leading, this is downstream of the leading edge, but anyway. So you can see that we are capturing the behavior quite well. The differences that you are seeing is due to uncertainty in the measurements and some uncertainty in now being able to capture the correct inflow boundary conditions. The inflow boundary, I haven't said anything here, but the inflow turbulence, we use some kind of a synthetic turbulence generator to generate the inflow turbulence that matches the characteristics of the measured turbulence in terms of the intensity and the length scales. The length scales are important here, so we do that. All right, so that's so I have a few minutes to talk about the semiconductor chip cooling. I'll go through this quickly. As many of you might know, semiconductor chip cooling is an important problem. The chip market is increasing very rapidly, and a lot of the companies all around the world, from Japan, Taiwan, Korea, US, etc., are working very actively to try and address the chip cooling market, particularly driven by AI, which requires very high computing power. So in order to cool these advanced chips, people are looking at liquid cooling. Here is a configuration of liquid cooling that we are doing with support from Department of Energy and the ARPA-E programs. And here, basically, the idea is to have an array of micropillars on this die. There is a thermal interface material here. There is a heat spreader here. This is a copper block, and etched into this copper block are these micropillar arrays. Liquid coolant is being delivered. Liquid coolant, in this case, typically being a refrigerant, is being delivered by a plenum and delivery channels into the bottom of the micropillars, and the liquid rises up along the micropillar, pins at the inner edge of these micropillars, and then expands outwards to pin at the outer edge. Most of the evaporation is taking place at the surface, and that is what is providing the cooling. At this stage, we are not looking at boiling. It's something we will look at further down the road, but we are mostly looking at the cooling at the top interface. So we are collaborating with some experimentalists at the University of Maryland. We have some experimental data for this micropillar array. Some simple experiments with the individual micropillar. This is the micropillar. The liquid goes up the micropillar and then pins on the inner edges and expands to the outer edges. All the calculations are done with OpenFOAM, transient 3D CFD, using a volume of fluid method here. And we have incorporated models for the dynamic contact angle model and evaporation of the interface. We have done some earlier work with a former student, Abhijit Karmakar, looking at falling film with evaporation, and you can see the agreement with experimental data. It's quite good. So now we are comparing with experimental data for this particular geometry, both unheated, this is the unheated micropillar, and these are heated micropillars with evaporation. For the computational models, we are using a dynamic Kistler contact angle model. We have some flexibility in making adjustments here in terms of advancing and receding angles. I won't talk too much about that. This is fairly standard, incorporating the surface tension forces at the interfaces. And for the phase change, again, we are looking at a couple of different models. The very commonly used Schrag model, which is basically a kinetics-based model, and there are some coefficients here that need to be looked at, and we also looked at a simplified form of a diffusion-based evaporation model. So looking at two different evaporation models, some modification of the contact angle models to see if we can get good agreement with data. So these are just visualizations, experiments at the top, and computations at the bottom. The liquid is going through the hollow micropillar. As I said, it pins on the inner edges and then expands out. So these are just showing you qualitative simulations of the simulation, and these are the experiments. The comparison is shown here. We're looking at the pressure difference, integrated pressure difference, average pressure difference across the interface as the liquid goes through the micropillar. So this is the liquid advancing through the micropillar, the pressure is increasing. This is where it reaches the top of the micropillar and pins on the inner edges. And then as it expands on the outer edge, the surface area expands, the pressure drops, and eventually it will reach the outer edge of these micropillars. And then eventually, if you keep pushing fluid, it will overflow into the region between the micropillars. Experimental measurements, some analytical results in blue, and our predictions in orange, they're all right on top of each other. So then we look at the heated micropillar. So now in this case, the micropillar is heated. You are looking at the interface moving up, and you're looking at the evaporation mass flux along this interface. So there's some interesting physics as the interface moves up. It's a hydrophobic surface. You have a concave interface in the middle. As it goes up, it pivots, the interface pivots into a convex shape, and then it moves out, and we're looking at the evaporation flux. So we're comparing the evaporative flux and the heat transfer coefficient. The solid black symbols are the experimental data, and the predictions are our line. Well, we also have symbols here, but these are the two colored lines with two different models. The agreement is generally good. We're still trying to tighten these up. The agreement is generally within 10 to 15, 16% with the experimental data. What you can see is within the scatter of the experimental data. Again, we are trying to tighten up these agreements to within 10%, which is very good for two-phase flow. This just shows you the various stages of the drop rate evaluation. So the eventual goal in doing all this calculation is because we really want to look at the entire rack. The rack consists of several servers. The servers consist of these cooled chips. So it's not possible to do the CFD calculations with the resolution needed to resolve all these cooling configurations. So we need to develop a neural network model for the cooling chips. That is why we are doing these detailed calculations. With these detailed calculations, we'll develop a training database. We also have experimental results. So we'll combine all this into a training database, and we'll look at neural network models, both a simple neural network model and also a physics-informed neural network model. These models will then serve as the representation of the CPU or GPU in the server model, and then we'll be able to do the CFD calculations and build a neural network model for the CFD, which then serves as a building block for the rack, and then you have a systems level code that can do the entire rack or the data center or cooling optimization. So that's the plan under this project. So I'll conclude here. I think I'm just on time, probably didn't leave time for questions. But just OpenFOAM is a very popular code. We have done a high Reynolds number calculation for Vane heat transfer with good agreement, and we are right now doing work on chip evaporative cooling, doing evaporation right now. We'll look at boiling in the near future. Thank you. I'm done, Somnath.
Thank you, sir. So today we had a panel discussion on OpenFOAM and in-house code, and probably your group makes a case on migrating from in-house to OpenFOAM. There are few questions. We'll take one or two. Did you consider Marangoni effect in the evaporative cooling, and how did you take care of the contact angle for the heated pillar case?
Yeah, so we do, as I said, we are experimenting with contact angle model. So that is still we are using the Chrysler contact angle model right now. Seems to work well. We do include Marangoni effects in our calculations.
Yeah. And for evaporative cooling, do you have any models to account for bubble microlayers? Are they publicly available?
You're talking about boiling?
Yes, for the evaporative cooling, do you have any models to account for bubble microlayers? It should be for boiling.
Yeah, there are, and we haven't done that yet, but that's something we will look at. So predicting nucleation is a very difficult problem. So any boiling calculations, you have to start with some initial distribution of nucleated bubbles. The real challenge is actually being able to predict the nucleation. So there are some recent studies where people have done MD calculations to predict the nucleation, but it's very difficult to couple the MD and the continuum calculations at this stage. So once you start with some distribution of nucleating bubbles, then there are number of studies that have looked at boiling in two-phase flows, even with OpenFOAM.
The other question I'm reading from the chat box is quite impressive work on turbomachinery blade cooling. How did you manage to incorporate fluid properties in OpenFOAM? I think this is probably straightforward.
Yeah, I mean, for turbomachinery calculation, fluid properties are fairly standard. I think we just input them for the particular. We're mostly using here gases, and so most of these calculations are done for air with some combustion gases. So those are relatively well known. So
I hand over to Chandan, and I think you are probably running out of time.
Yeah, I need to run.
Okay, thank you, Professor Acharya, for joining the session, and we really appreciate your time, and it was very insightful talk.
Thank you.
So let's thank the speaker on behalf of all the audience. Thank you very much.
Thank you. And if anyone has questions, they can email me, and if they are straightforward, I'll be happy to answer them.
Sure.
Bye.
Thank you.
Thank you, sir.
So I think I request Professor Roy to conclude today's session.
Yeah, so we thank you all the participants for being attending the online talk over such long duration. We also have another long day waiting for us tomorrow. We had a lot of interesting discussions today, starting from training in OpenFOAM, then Professor Gavin's talk, then our panel discussions, and looking into different modules of OpenFOAM, as well as looking into different applications of OpenFOAM. Hope this is of value for the participants spending entire day online today. And we'll have some other important talks, as well as we'll have few training programs, which are basically demonstration of OpenFOAMs tomorrow. So we expect to see you all online tomorrow. Tomorrow we'll start from 10:15, right?
We'll start from actually 10:15, yes.
10:15 Indian
I will
Standard Time.
post the schedule. I think it's given in the program schedule.
Mhm.
So
Schedule
yes,
is
I
there,
think
right?
we again thank you all, and please be with us tomorrow, particularly who are interested in the training programs. And we have multiple talks from PhD scholars throughout India and UK. So I hope it will be useful. Thank you all.
Thank you.
So we are closing the session today here.
Thanks.